In this video, we're going to introduce the concept of centripetal force. So let's say a person is spinning a rock attached to a string in the counterclockwise direction with a constant velocity. In previous videos, we know that the rock is going to have a linear velocity vector that looks like this in the magnitude of v, which we call our linear speed. And we know that in a few moments, a rock's going to travel all the way here, and its velocity is going to change direction, but still have the same magnitude. In previous videos, we explained that the reason the object is able to continue traveling in this uniform circular motion is because the object is accelerating radically inward. So at all points, the object is experiencing centripetal acceleration. If you remember from the last unit, we learned that Newton's first law of motion states that an object velocity will not change unless it experiences an unbalanced force. So in the case of our rock, we see that the velocity vector is changing. So according to Newton's first law, there must be some net force that is acting on our object. Well, with that in mind, we now approach the concept of centripetal force. And our centripetal force is going to be acting in the same direction as our acceleration. Because if an object is accelerating in the inward direction, the force must also be in the same direction, hence why we call it centripetal force. And remembering Newton's second law of motion, which states that the force is equal to the mass of the object times its acceleration, we can connect all this by writing that the magnitude of the centripetal force is equal to the mass of the object times the centripetal acceleration. Now that we have a clear understanding, let's look at some diagrams and try to identify the centripetal force. So in this diagram, we have some ball or pendulum that is attached to a string which is attached to the ceiling. And we see that the pendulum or this object is traveling in a circular motion. And we want to find the centripetal force. For the sake of it, let's jot down all the forces that are acting on our object. So if you remember the unit when we talked about forces and Newton's law of motion, we know that this object, as well as all objects on Earth, is going to experience the downward force of gravity. And since the object is attached to a string, there's going to be some pulling force that is acting on our object. And that force is called the force of tension. Now, this force of tension isn't directly counteracting the force of gravity. So we must break up the force of tension into its vertical and horizontal components. So we have its vertical component, and we have its horizontal component. And you can see that the magnitude of our centripetal force is going to equal the magnitude of the force of tension in the horizontal direction. And now we identified our centripetal force. Now let's look at one more diagram. And just for fun, let's say you are assigned an important mission to go to outer space and fix a broken part on a satellite. And we were wondering, what is the centripetal force that is keeping you and the satellite from drifting off in a straight line? Well, that's the force of gravity. And it is the force of gravity that's keeping you and the satellite on our orbital path. While you are there, you may feel like there is no gravity, but actually, there is no air resistance, and since you are in constant free fall, it feels like there is no gravity. So back to our problem. In this scenario, the magnitude of the centripetal force is equal to the magnitude of the force of gravity. So in recap, the centripetal force is the unbalanced force that is keeping an object moving in a curved path. And the centripetal force is also pointed in the same direction as the centripetal acceleration. And these two come straight from Newton's first law of motion. Lastly, the centripetal force is equal to the mass of the object times the acceleration of the object. And this comes from Newton's second law of motion. Thank you for watching this video and hope to see you next time.